So this problem is following up on that work we did yesterday. These are called optimization problems because we're always trying to get a maximum or minimum value for something out of it. Yesterday we took notes on the basic process. Basically we're going to turn this into a single equation, oftentimes by combining a couple equations into a single one. And then we'll find the max or the min of that single equation using the same techniques we know from general max and min, which is find the derivative, set it equal to 0, and solve from there. And that's our general idea. But of course that does mean we have to write the equations. And that's kind of the difference between these and just the basic max-min problems. Well, in writing the equations, a great way to start is by drawing out a picture.
Yes.
So in this case, we know it's going to be a rectangular area. And we need fence to notice only for 3 of the sides because the other side is bordering the river. And we're told specifically that it needs no fence along the river. So we don't need to worry about that part of it. Well, if we're going to be writing equations, I need some named quantities here. So I'm going to go ahead and be uncreative. I'm going to call this the width at W, and I'm going to call this length L for the length. And I'm going to call both those L, of course, because it's a rectangle. They both must be the same length. All right, we're going to write 2 different equations now. The first one involves the number that we're given up here, the 3,600 yards of fencing. So I'm going to do 3,600 equals what? And so you'll notice here, in order to find out that total length of fencing, it's going to be this plus this plus this. That's why it is going to be 2L plus W, yes. All right, then I need to write another equation. The other equation then needs to be what I'm going to be trying to maximize or minimize. So we're looking to see what are the dimensions of the largest grazing area. There's a key word there, area. So I need to figure out what the area of this is. So we're going to do area equals, and of course area of a rectangle is length times width, LW here.
That's what I did.
All right, those are my 2 starting equations. Now remember, I want to be able to combine these into a single equation. In order to do that, I'm going to solve one of the equations so I can write one variable in terms of the other variable. Notice one in terms of the other. So I go back to the equation that only has the 2 variables in it. So I want to go back to that first one. And in this case, I mean, technically I could solve for L or W, but solving for W looks a lot easier. So I'm going to do that. So I take that first equation, solve for W, and we should get W equals 3,600 minus 2L. Now, substitute that value into the area equation. So we're now going to do area equals L times, and now I replace the W with what W equals. So 3,600 minus 2L. I have the equation. Technically, I could go ahead and take the derivative right now, but it's going to be a bit harder if I do it right now. Because I'd have to use product rule and some stuff like that. Make your life a little bit easier. Distribute in the L first, then find the derivative. And so when we do that, you should get a derivative of 3,600 minus 4L. Now remember why we did that. We did that because we want to figure out where the derivative equals 0 to find that critical number. That's the local max or local min. So do 0 equals 3,600 minus 4L. Solve that for L. So I'm going to subtract 3,600 from both sides, divide both sides by negative 4. And you should end up with L equals 900. All right. Now, I go back at this point, and this is normally a great time to do it. Once we've solved for one variable, go back and make sure that you're answering the question that was asked. So this one is asking what are the dimensions of the largest area. So I'm not going to actually have to find what that area is, but I do need to know both dimensions. So I now need to solve this for W. Well, then I'm going to take this value for L, and I'm going to plug it into the equation that's solved for W. So plug in the L there. What does that give you? And so when I plug that in and solve it through, I end up finding that W equals 1,800. And so those are my 2 numbers. Although technically speaking, oops, erased too much there. Technically speaking, we do want to go ahead and include units on these. So both of these are in yards. Since we are dealing with actual questions that have units associated with the original values, remember to include those units in the end. So the stuff we give actually makes some sense. One thing to note here, yesterday we did a fencing problem as well, right? Yesterday it was a square. Notice if you had just assumed that this would be a square to optimize it, it wouldn't have been the case. The fact that we didn't know one of the sides threw that expectation off. So that's why I said yesterday you always want to check it. You actually need to go through the math, because there are certain situations where you can look at it and know, but a lot of them have a little subtlety like this in them that's going to throw that off. Now as you start looking at this problem and thinking it through, it's kind of hard to see right now. I mean, we know a coordinate plane, we can envision what this line would look like, we know where that point would be, but really being able to see it and put those pieces together would help. So I would actually even sketch the graph and put the point on there so we can see what's going on. But does this help? Do you now know what you would do with it? So as you look at it, if we're looking for distance between the line and the point, of course, to measure that distance, it's basically just saying, okay, how far is it wherever that point is? And we want to look for the shortest possible distance. And you might guess that it certainly would be something like that, but it's kind of hard to tell exactly where that would be. So we're going to have to do a little bit of work, a little bit of calculation to be able to start figuring that out. All right, so to do that then, well, this represents the distance, right? Well, how do we calculate distance between 2 points?
Distance formula. Acceleration.
Distance formula, yeah. Do you remember what the distance formula is? If you don't remember the distance formula, basically the distance formula is just a glorified version of Pythagorean theorem. So like, if I'm going to try to find that length right there, you know, I got a right triangle. And so I can find the hypotenuse of that right triangle by taking how far we go over and how far we go up. And then using that with Pythagorean theorem. So if I start doing that with this one then, d squared would equal a squared plus b squared, right? Well, that's got to be these two lengths. Well, if I want to know how far I'm going over, notice I'm labeling this point xy. How far I go over, how would I describe that length? It's 2 if we're going from here, from the axis, but what if we're going all the way over to where the point is? Well, if I want to know that distance, like let's say x was, this had an x-coordinate of -5. If the x-coordinate was -5, what would that length be? It'd be 7, right?
Really?
How could we get that? Well, basically you're just doing that x-coordinate, the difference, actually I should say, between the x-coordinate and 2.
2 minus 5.
So I'm going to go ahead and just call that then x minus 2. That'd be that horizontal distance between them. And again, we're using Pythagorean theorem here, distance formula, so that would be squared. Plus, how would you find that length? And so yeah, that distance there is going to be the y minus the -1, which of course then is y plus 1. And that's going to be squared. And so that would give us our distance. Now, of course, that's distance squared, right? We talked about distance formula. If you're doing this as distance formula, this is the only difference. Distance formula gives it to you with the square root over it. And so this is what we're really going to be dealing with here. Well, it looks kind of complicated at the moment, but we're going to be doing some simplification, which will kind of help and kind of won't. So let's go ahead and start going through that. So d equals. Right now, I can't yet take the derivative and have it be useful for me because I'd have to take the implicit derivative. And that's not going to help me in this case because I don't want multiple primes in it. So what I'm going to do then is just like we did on that last one, I'm going to replace one of the variables with what one of the other ones equals. And so you'll notice up here, we combine our two equations. I know what y equals. So I'm going to plug that in for y. And so my equation now is going to be the square root of x minus 2 squared plus, now I'm plugging in what y equals for y. So I'm going to replace the y with 3x plus 4, and then that is plus 1 squared. So notice, this 3x plus 4 right here came from this 3x plus 4 there. This is where we do that substitution piece like we've done on some of the other ones. That's, in many ways, the hardest part of this. So from here, let's do a little bit of cleanup. Please square out and simplify everything inside of that big old square root. So this is what we're looking at when we just square out everything on the inside and then combine your like terms. There we go. Yeah, there was a correction there. Should be a 25 on the end, not a 1 there. And so then when we combine our like terms, we're looking at this. Now notice we got a single equation that represents distance, all in terms of x. So wherever that equation is going to be minimized, that's going to be the smallest distance. So we're now at the point of finding the derivative. But I'm going to try and make your life a little bit easier here. The point that minimizes our square root equation here, wouldn't that be the exact same thing that minimizes the quadratic on the inside? Does the square root change where it would be minimized? And so because of that, yeah, we can go ahead and we can get rid of that square root and really just find the derivative of 10x squared plus 26x plus 29. So go ahead and find that derivative and then use it to find your minimum from there, because we've done all the hard work. Now it should be the easy stuff from there. All right, so when we work it through, we get negative 26 over 20, which is negative 13/10 if you give it as a fraction, or negative 1.3. Now remember, that is our x value. So we're asked in this problem, remember, what point on the line gives us the closest one. So I haven't got my full coordinate pair yet. I still need to find out what the y coordinate is. So we plug this number in. Now, again though, with the work that we've recently been doing, one of the big questions is always, what do I plug it into? Am I going to plug it into this equation? No. Because remember, d gives me the distance. Would I then plug it into the derivative? No. I need to plug it into the original equation. That is the equation of the line right here. And so I'm going to do y equals 3 times the negative 1.3 plus 4. And then whatever that gives me is going to be my y coordinate. So that's going to be negative 3.9 plus 4. That is 0.1. And so the actual answer to the problem then is negative 1.3, comma, 0.1. That is the point on that line that is closest to the point that we are given. Now, there's a lot of work in this one, right?
Yeah.
That being said, can you imagine how the work changes when it's no longer the point closest to the line, but instead is the point closest to, say, a quadratic or a cubic function or something like that? It can certainly get more complicated because as we're looking at our distance formula, all of a sudden we can easily come up with much bigger powers in here. Now, it is possible to do. The process is the same, but realize that you'd end up with some really big polynomials in those sorts of cases.
Can you do it like
Now, once you've written this down, step one, because it's a big word problem like this, draw a picture of it. So if you haven't yet, draw a picture of the situation and label your dimensions on it. That's going to be especially useful in this one because there's a little detail that you might overlook, and I want to make sure you catch it. So first thing we do is we draw a box, right? A rectangular prism. Now, I want to start labeling my dimensions on it, but I'll tell you there is one pitfall that people can easily make, where we end up going width, length, height, and then we start working from there. But if we do it this way, it's going to be way more complicated than it really needs to be. Because you'll notice, yeah, has a square base. So we don't need width and length to be separate items. We need those to actually be the same. Now, you can call them both L, you can call them both W, you can call them both X even, I don't care. I'm going to call it W just because. And then we still need H for the height though.
Wait, so what'd you put?
Now that we have this, write an equation that involves the 32,000, please. All right, so for the 32,000, that's the volume. Volume is length times width times height in a rectangular prism like this. Of course, the length and width are both W, so W times W is W squared. And then that's times the height still. All right, so we got the equation that uses the original number. Now we need one more. Notice what we're being asked to find. We're looking for the dimension of the box that minimize the amount of material used. Amount of material used, that's basically surface area of this. But of course, remembering that this has an open top, so we don't want to count that top side as we do it. So, my surface area, I'll go ahead and just call it A. You call it SA if you want. I just never liked the two-letter variable names. So A is going to equal, let's do the bottom first, just so we remember not to double that one up. So that's going to be W times W, so that's W squared. Plus, now I'll do the front and the back. So notice the front is W times H. The back is also W times H. So that would give me 2WH. And then I have to do the sides, right? Well, that is also W times H. So rather than having to do 2WH plus 2WH, let's go ahead and then just call it 4WH. Now we have an equation for our surface area, which is what we're going to be trying to minimize. Now we're going to make our lives easier here if we solve it for H. So I divided both sides in that original equation by W squared, and then I'm going to take that and substitute it in for H in the other equation. Now when you plug it in though, notice we can simplify. We can actually simplify two different things. We can do the 4 times the 32,000, but notice we also have a W here that's going to cancel with the W there. Do that simplification and combining before you go and start taking the derivative. It's going to make your life a lot easier. All right, so we find our derivative. Notice this is the same as times W to the negative 1. And so that's why we end up with a minus here and a negative 2 there. All right, now this is what we're going to then try to minimize. Or rather, the derivative that we need to set equal to 0. There we can say it right. And so then solve that equation through from there. All right, so we solve it through. We figure out what W equals then, and so we have W equals 40. So we know the dimensions of our box that we're asked for are going to be 40 centimeters by 40 centimeters, because notice both of those are W, by one other. And so we now need the height in there. So I need to actually plug that back in and find out what the height is. So I'm going to plug it back into the height equation. So we're going to do H equals 3,200 over W squared. So that's going to be over 40 squared. Solve that through to figure out what H is. And so then when we solve that through, we should find that H is going to be 20. So we get 20 centimeters. So for this one, we know that we're going to have a poster, so I might start by drawing a poster. And we want to find the dimensions that maximize the printed area, where the printed area is like this inner portion, a rectangle within a rectangle, and there's some margins around the outside. And those are the parts that we know. So I make a drawing of it, and in this, I know that we have blank margins of 10 centimeters on the top and bottom. So I know that this is going to be 10, and that this is also going to be 10 here. We have a margin of 6 centimeters on the sides. So no, that's going to be 6, and that's going to be 6 there as well. So we want to find the dimensions of the poster that maximize the printed area. Well, let's start with the equation that involves the number we haven't used yet, the 6,000. That's the total area of this. We need some names for these sides then, don't we?
Let's do K and E for kind of.
I'm doing width and length, just to be uncreative about it.
What did you say, Marina?
And so to find the area then, I know that that's going to be 6,000. The area is just width times length. So this part's fairly straightforward. But then, the other one, we want the dimensions of the poster that will maximize the printed area. So that's the printed area now. So I'm going to say the printed area, well, that would be this length times this length, right? All right, let's start with where W was. Let's go with this length right here. Well, we know that that's W
W minus 12.
minus how much?
12.
Yep, 12. Because you notice we have a 6 on that side and a 6 on that side that both have to be taken out of W. So we're going to be doing W minus 12 here. And then that's going to be times the length of the printed area. So that'd be the total length, L, minus our margins total, which is going to be 20. So L minus 20. We now have our two equations. Now that you have your two equations, proceed as normal. Solve one of them for a variable, plug that in, then clean up that equation, find the derivative, set it equal to 0, and use that to find our minimum, or maximum in this case.
L equals.
All right, and then when it's all said and done, we found that W is 60 and L is 100.
Yep.
And so we're done.
I got